Hey, Wheaton North, Mr. Yergler here. We're going to talk about limiting reactants. We've actually already talked about this a little bit, kind of in passing, and it's something you already know conceptually, but we're just going to put some terms to it and do a practice problem with it. So limiting reactants you saw when you made s'mores in class. There was one of the three reactants, Teddy Grahams, chocolate chips, and marshmallows, that you ran out of first. You calculated how many s'mores each reactant would make, and you took the least of those. You just kind of knew intuitively that it would make the least. You would actually physically make the least number, right? Because you're going to run out of one of them, and so you're limited by that one reactant. And we call that a limiting reactant. It's the reactant that limits how much product you're going to make. So as soon as you run out of it, it's the one you're running out of first. And as soon as you run out of it, the production stops, the reaction stops. Because the limiting reactant is consumed. As soon as you run out of Teddy Grahams, you're done making s'mores, right? You can't make any more. The other reactants are left over. They're called excess, meaning that you have extra ones. So if you run out of Teddy Grahams, for example, you have extra marshmallows and chocolate chips, and it doesn't matter how many you have, you're still done making s'mores, right? You can't make any s'mores because you're out of Teddy Grahams. The excess reactant will just remain there. That's what this picture is kind of showing. After you react all of the green, you have a little bit of this orangey red color left over, right? This is excess reactant. This was your limiting reactant, right? And then now you have products, okay? A good example of this is anytime you're making anything, putting pieces together. So we're going to call this Santa's dilemma. Let's say he has 8 car bodies and 48 tires, and he wants to make cars. Obviously, there's only going to be 4. There's going to be 4 tires per car, and so he's limited by the number of car bodies he needs. Right? It doesn't matter how many extra tires he has. He's done after he makes only 8 cars. Right? So which one limits the amount of cars he can make? The bodies does, because that's what he's going to run out of first. The excess reactant is the one that he has extra of, in this case tires, right? So he's only going to use enough tires to fill out his 8 cars. And those are your excess reactants. You still have leftover tires after you're done making the cars, the products. Now, let's say he makes a different toy car, where it takes 4 wheels, 1 body, and 2 decals, 2 little stickers to make 1 car. If he has 58 of everything, that doesn't necessarily mean that he's going to make 58 cars, right? And it doesn't necessarily mean that he's going to use all of his materials. We have to individually calculate each of them. How many cars can he make with his 58 wheels? How many cars can he make with his bodies? How many cars can he make with his decals, right? So if you were to calculate that out, we would probably use a proportion. 58 wheels makes 14.5 cars. We'll work with 14.5 because in chemistry we're always going to have decimals, and that's fine. In this particular case, it would really only be 14 cars. But he has enough bodies to make 58, and he has enough stickers to make 29. But in reality, he's really only going to make 14, right, or 14.5. And we do the same thing in the calculation with the Teddy Grahams and the s'mores. We calculated how many we could make with each thing, and then we took the smaller amount because we were going to run out of one of the things first, right? So let's talk about how do we solve a limiting reactant problem. You first need to use stoic to calculate how much product you're going to produce from each reactant, right? Just how we calculated how many s'mores we could make from each ingredient. We also need to calculate how many moles or grams of a given product we're gonna produce from each reactant, right? So you're going to do a couple different calculations, or you're going to do it a couple times. You have to pick you have to calculate the same product, right? If there's 2 products, you're going to have to pick one and calculate how much of that is produced from each reactant separately in order to figure out how much would actually be produced, right? It's going to be the smaller of the 2. The reactant that produces the least, you're going to pick the smaller one, is going to be the limiting reactant, and that's going to be the amount that you actually make, right? So let's say that one reactant is enough to produce 10 grams and one reactant is enough to produce 15, you're actually going to produce 10 because you're going to run out of that one first after you make 10 grams of product. So let's look at an example. Here we have our balanced equation. So this is in moles, right? And we have 2 separate givens, right? Anytime, write this down because this is where people get confused a lot. If you have two givens, you're going to have to do two calculations. Two givens, two calculations. We have 2 grams sample of ammonia, that's the NH3, and 4 grams of oxygen, that's the O2, okay? And I would actually circle or underline this or draw an arrow to kind of connect. The 4 grams is of this reactant and the 2 grams is of this reactant. So we have 2 reactants. We need to figure out which one is going to produce the smaller amount of product, all right? Now, in our balanced mole reaction, we've done these tables in gram stoichiometry. This can just be the balance. This is just straight from the balanced equation, right? And then down here, we're going to do our molar mass. So nitrogen is 14, hydrogen is 1, and there's 3 of them, so that's 17. Oxygen, it's O2, and so it's 16 times 2, that's 32 grams per mole. And then nitrogen monoxide, 14 plus 16 would be 30 grams per mole. Okay. Now, I'm going to only choose one product. Let's capture that in our notes as well. You're only choosing one product, okay? And it doesn't matter which one. However, I know that the question is later going to ask me about this one, so that's why I'm choosing that one. All right, so now we're just going to calculate down. 4 moles at 17 grams per mole is going to be 68. 5 times 32 is 160, and 4 times 30 is 120. Okay. Now, this is our balanced gram reaction. This is our proportional relationship that we're going to use in our conversion. So now let's go back to our givens, right? Let's start with the NH3. We have given over our goal. Our goal is the grams of nitrogen monoxide, right? The product. We want to know how much product is going to be produced, and we have 2 grams of ammonia. So that's going to be equal to the relationship between these two substances. Notice I'm keeping my units the same on top and bottom, right? Grams of ammonia, 68 grams of ammonia, and 120 grams of nitrogen monoxide. Notice that this whole side is coming from the balanced gram reaction. Okay, solve that, and X ends up being 3.5 grams of nitrogen monoxide. All right, now we're not done yet. We got to do the oxygen. We got to do the other one. We have enough ammonia to make 3.5 grams, but we also only have 4 grams of oxygen. Let's see how much that produces. 4 grams of ammonia, I should have changed this. Scratch that out, that should be oxygen. 4 grams of oxygen over X grams of nitrogen monoxide. And now I'm going to pull my proportional relationship between oxygen and nitrogen monoxide from my balanced gram equation. All right, so 160 over the 120 grams of nitrogen monoxide. Cross multiply and divide, and your X is you're gonna produce 3 grams of nitrogen monoxide. So now let's take a step back and think about what this is telling us. We're not going to produce 6.5 grams, right? That's not what this is saying. This is saying that we have enough ammonia to make 3.5, and we have enough oxygen to make 3. So how much are we actually going to make? We're actually only going to make 3, because at that point we'll run out of oxygen. We won't have any left. Even though we have extra ammonia, we don't have any oxygen to make any more nitrogen monoxide. Okay. So what is our limiting reactant? If we have these 2 reactants in this reaction, your oxygen is going to be your limiting reactant. Now notice we have more oxygen, right? We have 4 grams of oxygen versus the 2 grams of ammonia. Even though we have more of it, it's still limiting, because if we go back to the previous slide, they have different molar masses, they have a different mole ratio. It's 4 to 5, right? So that's not even either. So you actually have to do the calculation. You can't just look at this and say, well, we have less of this, and so that's limiting. That's not necessarily true. We have more oxygen, but that's limiting because we run out of that first in the reaction. How much would actually be made? That's the 3 grams from the previous slide. Okay, so that's just one problem, one example. We're kind of really pulling all this stuff together. We're doing gram stoic, and then also figuring out limiting reactants. And then we could also do percent yield from there too. So that's limiting reactants. If you got confused on any part in the last slide on the calculations, I would write your question down right now. If you're confused on molar mass, write a question about molar mass. How do you calculate molar mass, or something like that? Okay. Make sure you have those questions so that you can get those cleared up in class. That's what class time is for. All right. We'll get more practice in class as well. But this is Mr. Yergler signing off.